We are going to be looking what derivatives tell us about the shape of a graph. We first want to talk about the first derivative and how it can help us with curve sketching. So what does the first derivative tell us about the shape of the graph? Let's look at a function and look at the derivative. From a to b, we see this function is increasing, and we see that the derivative is always positive there. From b to c, we see that this function is decreasing, and we see that the derivative between b and c is always negative. And from c to d, the function is increasing, and we see that the derivative, the slope of the tangent to the curve there, is always positive. Tangent lines have positive slopes, and the function is increasing. When the tangent lines have negative slopes, the function is decreasing. Let's see how we can officially define increasing and decreasing by looking at some monotonic functions. Mono means one, and a monotonic function is a function that just does one thing, meaning it's always increasing or it's always decreasing. So here is our always increasing function. So we can define that to say that it's increasing if the function value at x2 is always greater than the function value at x1 when x2 is greater than x1. Similarly, to define a decreasing, the function value at x2 is always less than the function value at x1 if x2 is greater than x1, and that tells us our function is decreasing. So what about the derivatives? Well, we see the derivative here is positive. We see the derivative here is negative. So we've got a theorem that tells us a test for finding these intervals of increase and decrease. Suppose f is continuous on a closed interval and differentiable on every interior point of the interval. If the derivative for every x on the interior of the interval is greater than 0, then the function is increasing on the interval. If the derivative for every x in the interval is less than 0, then the function is decreasing on the interval. We're going to prove this for the first case, and the second proof would be very similar. So we're going to assume that for all points on the interior, so on the open interval, that the derivative is positive. It's greater than 0. So we're going to let x1 and x2 be in the open interval from a to b, and x2 is going to be greater than x1. Well, we know that the derivative for x's on this interval is greater than 0. That was our assumption. And so if the derivative is greater than 0 for all points on this interval, then we know that it is differentiable for all points on the interval. Well, differentiability implies continuity, so if it's differentiable for all points, it is continuous for all points. So on the interval from x1 to x2, this function is continuous and it's differentiable on the open interval from x1 to x2. Therefore, we just met the conditions for the mean value theorem, so the mean value theorem applies. So by the mean value theorem, we know that f of x2 minus f of x1 equals the derivative at c times x2 minus x1 for c in that interval. So we're looking from x1 to x2. We know the derivative is positive for every point in this interval, and so since c is in this interval, the derivative is going to be positive here. We also know this difference here, x2 minus x1, is positive because x2 is greater than x1. So we know that f of x2 minus f of x1 equals a positive, so therefore it's greater than 0. Now let's go ahead and move the f of x1 to the other side. And we have that f of x2 is greater than f of x1 for every point in this interval. Well, that was the definition for increasing. So therefore, f is increasing on this interval. And that was what we wanted to prove. Now the second one would be very similar to this, but using a less than 0. Is the converse true if we turned it around? If the function is increasing on the interval, then is the derivative always positive for any point on the interval? You may be tempted to say yes at first glance, but let's look at x cubed. Here's the graph of x cubed. This is a monotonic function, always increasing. However, the derivative equals 0 right here at 0. So this converse is not true. This is called a saddle point because the function was increasing. The derivative is now 0, but the function is still increasing. Let's sketch a function that is continuous on the domain from -infinity to infinity that satisfies the following conditions. So we need the derivative greater than 0 on these intervals. So let's go ahead and make us a sketch here. And it looks like we're going to look from -infinity to 0, then from 0 to 4, then from 4 to 6, and then from 6 to infinity. The derivative is positive from -infinity to 0. So that tells us the function is increasing on this interval. From 4 to 6, the derivative is positive. From 6 to infinity, the derivative is positive. The derivative is less than 0, so negative from 0 to 4. So the function is decreasing from 0 to 4. The next condition, the derivative at 0 is undefined. So the derivative right here, if it's undefined, I'm just going to make a little cusp there because this is undefined there. Next condition, the derivative at 4 equals the derivative at 6, and they equal 0. So the derivative is 0 right here. The derivative is 0 right here. Let's see then, and this function could have any kind of a vertical shift because we don't have any information about some starting point. So we could just start it somewhere here and say the function is increasing and then it's decreasing, but it's undefined at 0. So let's make it increasing and then decreasing, but undefined right here at 0. So we made a cusp. Then at 4, the derivative is 0, and then it needs to increase. So we're going to turn like this, and we see that we have a local minimum there. Then the derivative is 0 at 6, but then it's increasing again. So we have a saddle point right there. So looking at the signs of the derivative, whether it's positive or negative, is going to help us to identify local maxima and local minima. If we have a local minimum at C, to come down to a minimum here of this continuous function from A to B, the derivative must be negative here so that the function's decreasing. Then the function needs to increase after this and the derivative must be positive. So if we had a critical number at C and we checked the derivative to the left of C and to the right of C and we saw that the derivative was negative and then the derivative changed to positive and was 0 at C, we would know that we have a local minimum. Similarly, for a local maximum, if we had a local maximum at C, this is a continuous function from A to B, if the derivative here, if this is going to be a maximum, then the derivative here needs to be positive so that it's increasing, then it needs to decrease after that, and so the derivative would be negative on the other side. So let's look at this function and let's identify all of the critical numbers, and let's look at the signs of the derivatives. So critical numbers would occur, or critical points. They're kind of used interchangeably. Some books call them critical points, some call them critical numbers. So these critical points would be at places where the derivative equals 0 or it's undefined. Well, the derivative equals 0 here, 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 and here because we have horizontal tangents at those places. The derivative is undefined here because of the cusp. Identifying any absolute maxes and mins, we see there's an absolute minimum at this endpoint, and we see that the absolute maximum occurs at this cusp. Now let's look at what happens to the function from A to C1 and correlate that with the derivative. Well, the function is increasing here. The derivative is positive. So a derivative positive on this interval would tell us the function was increasing. The derivative here again is positive, and so as we look here, the derivative was positive, it was 0, it was positive again, it didn't change signs. This is a saddle point, it's no extreme value. Let's look at the function here. We see that we have a negative slope. The derivative is negative. The derivative was positive, then it was 0, then it was negative. That's a way to identify a local max. Looking here from C3 to C4, we see that the slope of the tangent here is positive. The derivative is positive there. The derivative was negative, 0, positive. That's how we can identify a local min. Derivative from C4 to C5, the function is decreasing. The slope of the tangent is negative. The derivative is negative. Positive to negative, we have a local and an absolute max right there. Last interval from C5 to B, the function is decreasing. That slope of that tangent is negative, and we went from a negative to 0 back to negative. That's a saddle point, no extreme value. Let's summarize this. It is what we call the first derivative test. Suppose that f is a function on an interval that contains a critical point c, and assume f is differentiable on the interval except perhaps at c itself. So it's okay that it's undefined right at c. If the derivative changes sign from positive to negative, so if you think about that, positive to negative, then we have a local max. If it changes sign from negative to positive, then we have a local min. If it doesn't change sign, then we do not have an extreme value. So that's just summarizing what we saw there. Positive to negative, local max. Negative to positive, local min at C. Positive to positive, nothing. Negative to negative, nothing.